All right, so we looked at the binomial distribution and said what happens when n gets large. When n gets large, the calculations get to be a little bit more complex, but de Moivre comes to the rescue with the normal distribution. Poisson asked a slightly different question. He said, all right, if n does get large, but not just n getting large, let me look at p also, because p might cause some problems in the calculations too. And if we make p tiny, 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 then we're also going to have problems in our calculations. But he says, okay, look at the situation where p gets tiny and n gets large. So let's look at n times p, which is the mean. Let's look at the situation when that is reasonable. So, for example, think of an intersection in the road. So you've got an intersection in your town, and the probability of there being an accident in that intersection is going to be negligible. If you watch the intersection for 10 minutes, chances are there's not going to be an accident there, depending where you live, of course. But chances are there's not going to be an accident there. But if you look at it for long enough, say for a year, maybe you will have, let's say, 2 accidents a year, something like that. Okay? So there is a situation where you can watch it for a long, 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 long time. So your n is extremely big. Your p, the probability that you have an accident in any one of those little n segments, those n segments could be 10 seconds long. Probably you have an accident in any one of those 10 seconds, extremely small. But the product, huge n times little p, to represent what happens in a year, can be reasonable. So this is what Poisson did. Poisson said, all right, here are the conditions, we'll set them up. That the probability that an event occurs in an interval is proportional to the length of the interval. So if I watch it for twice as long, then my probability is going to be twice as big that I will observe an accident. To make the mathematics possible, an infinite number of occurrences are possible. We know that can't happen, of course, but we'll see in a minute that that's not that big an assumption. The third assumption is a big one, and that is that events occur independently. Okay, so if we're watching the intersection and there was an accident yesterday or the day before, that's not going to make any difference to whether there's an accident today, let's say. So there is a certain amount of independence. Once again, this is taking a mathematical idealization, the model, and applying it in a realistic situation, reality. And so we have to practice our art to see whether we're doing things appropriately or not. But anyway, so these are the 3 assumptions that Poisson came up with. And this rate, lambda, is the average rate, let's say per annum, every year, that we're operating in. Okay? And then the probability of having X events or accidents is given to us by e to the minus lambda, lambda to the x, divided by x factorial, and plug in the appropriate x that you're interested in. Wow, look at this. It's only got a single parameter. It's only got lambda. It occurs in 2 places, sure, but it's a single parameter. That's the beauty of the Poisson distribution. Now, it's strict. The conditions are strict for the application, but if you can apply it, then you only need specify 1 parameter. So if we're going to use this as an approximation to the binomial, how do we relate things? How do we relate things together? And the answer is this parameter, lambda, the rate parameter, is the same as the mean in the binomial. Remember how I started all this by saying n gets huge, p gets tiny, but their product remains constant. So as n gets huger, p will get tinier. That's the mean. Now, if you do that, then you'll also see that the variance in the binomial, which is np times 1 minus p, is approximately np, when p is extremely tiny and the product np is constant. So that this lambda serves two roles in the Poisson. It is both the mean and the variance. So this is why very often we use the Poisson model when the variance goes up with the mean. So if we're in situations where the variance goes up with the mean, that's a tip-off that the Poisson might be a good approximation. It might be a good model to approximate things. So let's go back to that idea of an accident. So suppose the probability of an accident in a year is 0.00024, extremely tiny. We could do the binomial with this. It's extremely tiny. Now let's look at a village or a town where we've got 10,000 people. So n times p, 10,000 people times the point is 2.4. So we expect, on average, 2.4 accidents per year. So if we fit a Poisson to this situation, then the probability that we have 0 accidents in a year is e to the minus 2.4, 2.4 to the 0. 0 factorial is 0.0907. So that's like 0.1. That's like 1 in 10. So 1 in 10 years, we expect to have no accidents at that intersection. What about the probability of 1 accident at that intersection? Now we're talking about 0.2177. So that's roughly 1 in 5. So every 5 years, we expect 1 accident at that intersection. And so on. We can calculate this for the other x's, and here's what it looks like. So the most popular value is 2, and then things tail off after 2. And you can see it's essentially 0 by the time we get to 10. So the fact that theoretically we can go to infinity is not a big deal, because we've got most of the probability mass before 10. So that's the Poisson distribution. So far we've said the binomial. Okay, we've got the binomial, that's fine. Then we say if n goes to infinity, not saying anything about p. If n goes to infinity, then we've got the normal distribution. De Moivre showed that. And now we've said, all right, if n goes to infinity, but in the strange sort of way that at the same time as n goes to infinity, p goes to 0, so that their product remains constant, then we've got the Poisson distribution. And here it is for this situation when, of course, I'm not going to do the calculations by hand, you know that. We're going to go to Stata, and the function is called Poisson p, and here it is for lambda equals 2.4, and there it is. This is the plot of the Poisson that I just showed you.